Okay. So, go ahead and pull one out here for myself. All right. So, first of all, notice that this is number 6, okay, which means as during the, I believe it should be during the calculator active section. I think that's the calculator active section, okay, of the free response test, okay, or free response portion of the test there, okay. You'll notice that if you kind of flip through here real quick, you know, well, this is a question 3, but then this one's a question 6. This one's a question 6, this one's a question 6, so you kind of see a pattern there. It's like, these like to show up at the very end. This one's a question 6 as well, okay? And when we go to do our review, you'll see these are very typical kind of like last question problem, okay? And what that means is sometimes people are exhausted by the end or just so kind of burnt out with it by the end of the test that they, you know, don't do very well on it, which is good for us because that means we can get some points here and, you know, hopefully help us out as compared to, you know, the rest of the country and stuff like that. So, anyway, let's take a look here. So first of all, we're told that f of x is equal to the natural log of 1 plus x cubed. All right, and then we're told for letter A, the Maclaurin series for the natural log of 1 plus x is this. Okay, so we're told that that's really nice. And then we're asked to use the series to write the first 4 non-zero terms and the general term of the Maclaurin series for f. Okay, now, we're given the Maclaurin series for natural log of 1 plus x. We're trying to write the Maclaurin series for f, which is natural log of 1 plus x to the third. All right, so be careful there, right? When I first glanced at this, I was like, wait a minute, these are the exact same thing. Why did they give them this? But then I was like, oh yeah, there's an x cubed there, not just an x. Okay, so given that we have the natural log of 1 plus x is this, what do we need to do to make it the natural log of 1 plus x cubed? Exactly, just substitute in an x cubed. Exactly right. So for, I guess I call this 6a, maybe not 1a. Okay, but yeah, for 6a here, we'll just plug in an x cubed. So I'm just going to like go ahead and do that. So we'll have x cubed minus, and if you're okay with that, x to the 6th over 2, right? Plus x to the 9th over 3 minus x to the 12th over 3. 4, I mean 4. Brain fart there. Okay. But then, of course, those are our first 4 non-zero terms, right? 1, 2, 3, 4. But then we also need to write the general term here, all right? And you can, if you want, kind of put the plus dot 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 plus, okay, like this, and then just, you know, do what Mike said to do even in our general term here. So again, we'll just put in x cubed, so it becomes x to the 3n, right, over n, just like that. So there's letter A. Okay, pretty easy. And I believe that was worth 2 points. Well, at the end of this, we'll go through like the scoring guideline, just so you can kind of see like what points got you what, earned you what kind of thing. All right. Let's try letter B now. All right. Letter B. The radius of convergence of the Maclaurin series for f is 1. Well, that's kind of nice. Determine the interval of convergence. Show the work that leads to your answer. Okay. So we're given the radius of the convergence of the Maclaurin series for f is 1. Determine the interval of convergence. Show the work that leads to your answer. So they give us the radius of convergence here, and it's 1, and they ask us to find the interval of convergence. So typically when we do the interval of convergence, what 2 tests do we use? Ratio or geometric. But since we've got the radius of convergence here, and it's 1, do we need to use either of those 2 tests? We don't, right? Because what's the center here? What are we centered about? 0, right? There's no you know, shift one way or the other here. We are centered at 0, okay? It's not like x plus anything there. It's just, you know, what you can see in your Taylor series here, right? It's not x plus or minus anything in here. It's just x by itself. And so, right, we're centered at 0, which means then what will our interval of convergence be? Or I want to be careful here, but let's go ahead. So what would the interval of convergence possibly be, I guess I'll say? -1 to 1, right? Okay, but what do we still need to do? Test the endpoints, right, okay? Because, again, we didn't really use geometric or ratio test here. We're just kind of using the idea that since the center is 0, our radius of convergence is 1, we can just add 1 to 0, subtract 1 from 0, and that's our interval of convergence here. So we do have to check those endpoints. So we're going to check both of those. I'm going to check at x equals -1 and x equals 1. Okay, and again, that's just substituting in the -1 into our series here. Okay, and remember, we're checking it for the the radius of convergence for f. So it's f that we're going to be, oh, not f, sorry, the f that we wrote right here for letter A. Okay, so plug -1 in here for your general term, the sum of your general term for A. So we'll have -1 to the n plus 1, and then in the numerator, it'll be -1 to the 3n over, and then just the n there. Okay, now, we have two -1s there. We can combine them together by doing what? What do we do? Add the exponents. And so we'll get that -1 to the 4n plus 1 all over n. Okay. And because -1 is being raised to the 4n plus 1, what do we know about this series? It is not alternating. Very good. The power here will always be what? Right, it's always going to be, sorry, the power is always odd, so then yes, our answer is always going to be negative. Yeah, it will not alternate, So it's not alternating, but what can we determine about this series? Will it diverge or converge? Diverge, right, because p is equal to 1 there, okay? Okay. Actually, diverges p series, p equals 1 there. Okay, and then at x equals 1, okay, at x equals 1, we'll now plug in 1. And so it's the -1n plus 1, 1 to the 3n over n, which is then, again, 1 to the 3n is just going to be 1 no matter what. So we'll have really a -1 to the n plus 1 over n. Okay, what do we know about this series? It will what? It's alternating, and so therefore this is going to converge. And I should be careful there. Just because it's alternating doesn't mean it will converge, right? But if we check our two little characteristics, right, the limit of 1 over n as n approaches infinity will be 0, goes to 0, right? And then the next term will be smaller than the previous term. And so, yes, this is an alternating series. Okay, so it converges. Okay, and so we're going to exclude -1. We did, and then we'll just put a little equal to underneath the inequality there, and boom, there's our interval of convergence. Okay, so in kind of a clever fashion, they saved us some time here, right, in this problem. All right, so some of these problems normally take like a huge amount of space. This didn't take quite as much space, right? They were able to kind of like, we were able to bypass that initial ratio geometric test. And this happens sometimes on the AP test itself, where they'll take something that normally takes a lot of work, and then they'll give you some like information to then kind of bypass some of the earlier steps or something, and then, you know, proceed from there. Anyway, questions on letter B? Moving on. Okay, letter C then. Write the first 4 non-zero terms in the Chlorine series for f prime of t squared. Okay, if then, well, we'll get to the rest of that part there in just a second here. All right, so let's just write those first 4 terms. So again, we know f of x is, for the first 4 terms, it's approximately here, x to the 3rd minus x to the 6th over 2 plus x to the 9th over 3 minus x to the 12th over 4 plus ... You get the idea there, but we only need the first 4 terms, so we'll just write the first 4 terms for f. Okay, and again, where did I get these for f? It's just using that general term that we created right here. Okay, plugging in, you know, 1 and then 2 and then 3 and so on and so forth. Okay. And so then we will proceed here with then g, or sorry, f prime. Let's do f prime, right? Because we're trying to find f prime of t squared with the first 4 terms. So we'll do f prime of x then. And so again, we just take the derivative of each one of those terms. So 3x squared minus, let's see here, the 6 and the 2 will simplify to 3x to the 5th. And the 9 and the 3 will simplify to 3x to the 8th. And the 12 and the 4 will simplify to be 3x to the 11th plus ... All right. And then to find f prime of t squared, what does that mean we have to do now? Just, yeah, plug in t squared for all the x's. Yeah, so f prime t squared, again, is approximately, and I'm just going to go ahead and simplify my exponents too. So it'll be 3t to the 4th minus 3t to the 10th plus 3t to the 16th minus 3t to the 22 plus dot, dot, dot. Okay, so there's part of our first answer, or part of our answer right there. There's those first 4 terms, but we're not done yet. Okay, first 4 terms, but now we're asked if g of x is equal to the integral from 0 to x of that f prime of t squared dt, use the first 2 non-zero terms of that Maclaurin series for g to approximate g of 1. Okay, so in order to proceed here, what might be a good next step? What might be a good next step here then? G of x is equal to the integral. I'll go back up here. It says g of x is the integral from 0 to x of f prime of t squared dt. So what should we probably do next? Say again? Plug in x? Well, not quite yet. Remember, this is, yeah, exactly. Yeah, we want to take the integral first, and then we'll go ahead and substitute in the x. Yep. So let's go ahead then and find g, okay, which is equal to the integral from 0 to x of f prime of t squared dt, which is, in other words, the integral from 0 to x of 3t to the 4th minus 3t to the 10th plus. And since we're only really interested in the first 2 non-zero terms, I'm not going to worry about writing my other 2 terms here, right? We're only interested in the first 2 non-zero terms. So I'm just going to put plus, 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 and then dt there. Plus dot, 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 I mean. And then that. Okay. And so we're just going to integrate this, right? So integrating 3t to the 4th will become 3t to the 5th over 5, right? And integrating negative 3t to the 10th, well, that's just going to be negative 3t to the 11th over 11. Okay, and we're going to then, of course, dot, 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 and we're going to evaluate that from 0 to x. Okay? What's going to be true about our evaluation here for the lower limit? It's just going to be 0, right? All these terms these 2 terms have t in them, so they just disappear. And so we just replace all those with x's. So we'll say g of x then is approximately 3x to the 5th over 5 minus 3x to the 11th over 11. And we're not quite done yet, right? We've got our approximation for g of x. We want to use those to approximate g of 1. And so now what's left for us to do? Just plug in 1. You got it. So yeah, g of 1 is then approximately 3 times 1 to the 5th over 5 minus 3 times 1 to the 11th over 11, or in other words, 3/5 minus 3/11. Okay? Just like that. You can leave it like that. Yeah, actually, you could have left it right back here because it's kind of just arithmetic at that point. But so, either here or there, I'll say. Okay, one of those 2. Questions on anything up to that point? Pretty straightforward stuff, I hope. Okay. So then letter D. Letter D then. The Maclaurin series for G. So now we're talking about G. So that's one thing you got to keep track of here, right? We started with natural log of 1 plus x. Right, we were given that power series, and we had to manipulate that to create f, and then we manipulated f to create g, and now we're talking about g. So again, the nice thing is we're kind of progressing, and as we go, we're using the new thing in the next problem and stuff like that, and not going back to old stuff here. But Maclaurin series for g, evaluated at x equals 1, is a convergent alternating series with individual terms that decrease in absolute value to 0. So that's nice, right? Okay. Show that your approximation is in part C must differ from g of 1 by less than 1/5. Okay, so what is this letter D really asking us to find? Find the error, which then will require us to then use the next term. Right, okay? So we want to just figure out the error here and just show that it's going to be less than 1/5. Okay, so I'm going to set up that error here. So again, show that your approximation part C must differ. That means the difference from actual g of 1 by less than 1/5. So in other words, we're going to show here g of 1, actual g of 1 minus our approximation of g of 1, which is, whatever this 3/5 minus 3/11 quantity is, okay? That difference, we want that to be less than or equal to 1/5. Well, we know by our error approximation, okay, it must be less than or equal to the next term. What would our next term be here? Very good, okay? So how did you get that, Lander? What were you looking at?
I just went back up to the...
what we did right here?
Yeah, the f prime of t squared.
Okay.
And I just used this next term.
Right, so remember here, how did we get our first term, right? The first term for when we were approximating g of x, we just integrated this f prime of t squared, right? And put an x in the place there. We ended up doing the same thing for the second term. And so then to get our next term, our third term, that would be 3t to the 16th, integrating that, again, from 0 to x there, would get us then, yes, 3x to the 16th over 16. 17 over 17. Sorry, because we integrated it, my bad. Okay, so 3x to the 17 over 17, because again we're talking about g, which is the integral of f prime of t squared there. Okay, but we're not quite done yet, because what do we still have to do? What do we plug in here for the x? A 1, right, because we were approximating g of 1. And so this is, 3 times 1 to the 17th over 17, which is then just really 3/17.
How did you get 3x to the 17th?
Because so remember, f prime of t squared, we used the first two terms and we integrated those to get g of t.
Yeah.
Or g of x, I should say. When we are approximating our error here, we're approximating from g of x. And so it's g of x's next term that we need. This is f prime of t's next term. We have to integrate this to turn it back into g. Okay, does that make sense? So this is f prime of t squared. We have to integrate to get g. And so that's why we have that. Plugging the 1 in, you get 3/17, and is 3/17 less than 1/5? Well, if we cross multiply here, you get 15 is less than 17, so check. Okay, they are less than each other, or less than, yeah. Okay, so ta-da, it works. Less than 1/5. Okay, questions on any of that? Alrighty, so let's turn the page there. Take a look at this next one. Okay. Number 3, the Taylor series about x equals 0 for a certain function f converges to f of x for all x in the interval of convergence. All right. So basically, our Taylor series, right, converges to a certain function f. We don't know what f is necessarily, okay, but we do know some of its derivatives right here. Okay. The nth derivative of f at x equals 0 is given by this. Okay. Notice it's for n values greater than or equal to 2, though. So that means if we're trying to find the first derivative, okay, we can't use this, right? If we're trying to find the first derivative, because we only can do this for n greater than or equal to 2, and so the first derivative would be n equals 1. Okay. But then we're told here some more information. The graph of f has a horizontal tangent line at x equals 0, and f of 0 is 6. Okay. So we're given some other information there. All right. Letter A. Determine whether f has a relative maximum, a relative minimum, or neither at x equals 0. Justify your answer. Okay. So, how can we do this? Ideas here. Kara? Yeah? Okay, so we can use the first derivative test, see exactly. So first we want to identify, so I guess it's 0. Yeah, we'll see if the first derivative changes from negative to positive, okay, around x equals 0. Okay, well, if we, let's see here. What do we know about the first derivative? Not nothing. At x equals 0, the function has a horizontal tangent. So what does that tell us about the derivative of f? It's 0 at x equals 0. So, in other words, we can say f prime of 0 equals 0. Okay, so that indicates we have a critical point at 0, at x equals 0 for the function. But now when we go to talk about the first derivative, we're going to run our first derivative test, we're going to run some problems because we don't know anything else about our first derivative. This thing up here only describes things for our second derivative or third derivative, fourth derivative, so on and so forth. But what other method do we have? Go ahead, Nick.
Plug in a 2 for the derivative, you should get concavity.
Aha, so how can we use concavity to determine whether we have a relative maximum, relative minimum, or neither?
If it's concave up, it's going to be a minimum. If it's concave down, it's going to be a maximum.
Exactly. So we can find, again, we can use this because the nth derivative of f at x equals 0 is given by this. Okay? So all this can tell us is the nth derivative of f at 0, but we can use that second derivative test to determine concavity and then determine whether we have a relative maximum or relative minimum. Okay? So good job there. Right. So then f prime prime of 0 will equal, well, Now, how do we evaluate this? So what's going to go in for all my n's here? A 2, right? Because it's the second derivative. And so it'll be negative 1 to the third times 4 factorial all over 5 to the 2, and then 1 squared like that. Whoops, did I do? Sorry, 2 plus 1 is 3, not 4. So we get 3 there, 3 factorial. Okay. And what do we know about this thing? Positive or negative?
Negative.
Negative. All right. So f has a relative what? Maximum. Okay. That's all you have to write, really. Yeah, you don't need to write by the second derivative test or anything like that, because what you have shown here is sufficient for the second derivative test. You don't need to name drop the second derivative test. Okay? It's okay to just say first derivative is 0 at 0, second derivative is less than 0 at 0, therefore f has a relative maximum at x equals 0. Okay. Remember that the second derivative test, if you have a critical point, and then the critical point has a concave up or concave down, that determines whether you have a relative maximum or minimum. If your second derivative is also equal to 0, that means it is neither. Okay, neither. Okay, neither there. Or I should say inconclusive, maybe. Inconclusive, I think, is a better way to go. Inconclusive. Okay, inconclusive. So that's why you got to be careful there. All right, letter B. Write the third degree Taylor polynomial for f about x equals 0. Okay, so we are not given the series here. Okay, so one thing I want to be very careful to distinguish here. Here, okay, we were given like the general term. Okay, this was the general term for the Maclaurin series. All right, so like this is the Maclaurin series for that natural log of 1 plus x here, right? You can just for more terms, you would just keep plugging in different values of n. All right. Here, though, when we're trying to write the third degree, okay, this is not the series. This is not the general term. All this is the nth derivative of our function. Okay, so in other words, we have to go back to that original kind of formatting we had, where if we're trying to find it's centered about 0, it would be f of 0 plus f prime of 0 over 1 factorial x to the 1 plus f prime prime of 0 over 2 factorial x to the 2. All right, and I guess we have to do a third degree. So f prime 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 of 0 over 3 factorial x to the third. Okay, we are given different information to start out here. All we're given are these n derivatives of f. To write the Taylor series, we have to, then expand out using our more typical kind of format there. If there's some sort of pattern to this, right? If there's some sort of pattern to this when we simplify it and stuff like that, that, remember, is what yields this. Okay, this series here with the general term. Okay, so this is like the simplified version of what we just wrote using this particular function and stuff like that, and it results in this kind of like series. Okay, here we're not given information about the series, we're just given information about the derivatives, so we then use that to create a series and potentially, come up with a pattern or something like that. All right, so what is f of 0? 6. Okay, so again, rarely are you given these random pieces of information here and you don't use them, so we use that right there. Okay, what's f prime of 0? 0, so we can just put a 0 in there if you like, or you can just ignore it, kind of thing. It goes away, right? All right, f prime prime of 0. So I think it's negative 6/25. Oh, but when you simplify, I see what you're saying. It'll be, negative 3/25. Okay, so it depends on how much work you want to do simplifying or not. Okay, it's kind of your choice here. Again, f prime prime of 0, how do we figure that out? You just put a 2 in for the n here, and so then all these n's get to be 2's. Okay, and simplifying that, you're going to, your decision. I'm going to leave it less simplified just because. Okay, so it turns out this right here, right, that we were evaluating, turns out to be negative 6/25, but it's over 2 factorial there. Okay, and then x squared, and then f prime 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 of 0. So now we got to plug 3 in. So that will be, and this one I might be even less apt to simplify. So that's here. So 3 in there will be negative 1 to the 4 factorial over 5 to the third 2 squared all over 3 factorial x to the third.
Oh god.
Okay, and again, that's all this the crazy numerator here is coming from just this formula right here. I'm just plugging in 3 for the ends, and it gets us this. Okay, so you can simplify some if you wanted to, but it's not necessary. We can leave it, right? Because that's all we had to do is just come up with a third degree Taylor polynomial there. Okay, question, Lynn?
You said 5 cubed plus 2 squared. Is it supposed to be 3 squared?
It's n minus 1. So 3 minus 1 would be 2 squared.
That's right.
Yeah. Right, and it's a lot to keep track of here too. So I mean, feel free, I'm kind of doing this all, at once here, but feel free to do some side work if you need to, and then bring in your term there, because there's a lot of like little calculations. It's very easy to be thrown off by a little number or something like that, and then mess up. I mean, obviously you see me do it too, right? So, okay. Any other questions there? So far, so good. All right. Letter C. Find the radius of convergence of the Taylor series for f about x equals 0. Show the work that leads to your answer. Okay. So, we're going to find the radius of convergence for the Taylor series of f about x equals 0 here. All right. So, if you remember, right, we have our kind of like our derivatives here. If you were to kind of continue this out, so plus dot 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 here, plus the general term would be something like this: the nth derivative of f at 0 over n factorial times x to the n. Right? That would be kind of like our general term here, right? Extra general because I don't have the actual like function, the nth derivative there written in. Okay. So, if we're trying to find the radius of convergence, how do we go about doing that here? What should we do? Quit? How do we normally find a radius of convergence? What do we do? The ratio test. Yeah, okay. This thing's not geometric, right? So we have to do a ratio test here. Okay? So the ratio test is n plus, the n plus 1th term over the nth term, right? The next term over the previous term. I'm not going to do that, of course. I'm going to multiply by the reciprocal because this is going to be very messy already, and we don't need like fractions within fractions and stuff like that. Okay. So let's imagine here doing our next term. Well, that'll be then f, the n plus 1th derivative of f at 0, right, over n plus 1 factorial times x to the n plus 1. Okay, and then times, again, we'll do the reciprocal here, and I'll say then that's going to be n factorial over the nth derivative of f at 0, x to the n. Okay? So that's pretty tame, right? But now what do we have to do? Yeah, we got to simplify this. And of course, how do we evaluate the n plus 1th derivative of f? We get to use this. So everywhere you see an n, replace it with n plus 1. All right, and we're going to write that back in here. Okay, so.
Thank God.
Yeah. It was like some of these earlier problems are just too easy. We need something a little more, challenging is what you're trying to say. I got you, yeah. So, n plus 1 derivative, that means it will be negative 1 to the n plus 2, parentheses n plus 2 factorial, right? Over, and then I'm going to put that n plus 1 factorial in here with the 5 to n plus 1, all that jazz. So we'll do it here. So 5 to the n plus 1, n squared, and then I'll put the x to the n plus 1 up in the numerator here. Okay, so let me just pause right there so you guys kind of drink that in, okay, because there's a lot that just happened there. Okay, so there's my x to the n plus 1, and there's my n plus 1 factorial right there. Okay, and then from my f of n plus 1, right, so this is like, so this is the substitution right there. Okay. All right, so can we see all that that's going on there? Let me see if I can zoom out and show it. Yes, Kara, question?
Would it be easier to simplify like the x to the n plus 1 and then the x to the n?
It might be, off right at the bat. Maybe not a bad idea. So you're saying let's go ahead and cancel the x to n plus 1 and the x to the n like that, and so just make this x to the 1 right here and kind of ignore that?
It would just really point less to
Yeah, I think that's good. And we could also then do the same thing with the factorials too, right? Instead of n plus 1 factorial, n factorial, we could just say, okay, well, these will simplify to just be then that n factorial is going to go away. We're just left with n plus 1. So yeah, you could there. And then that would leave no factorial up here. So then we're just going to have, again, just the reciprocal, and then x to the n canceled as well. Cancel that, and so we're left with just a 1 there. Okay, so yeah, that's not a bad idea. Because this thing's already going to be a mess to simplify, so why not simplify it a little bit ahead of time first? And then we'll do the reciprocal of that nth derivative, okay? So again, this kind of canceled out here with that, okay? And so then we're left with just the reciprocal of the derivative, 1 over that nth term. So that's going to be then 5 to the n minus 1 squared in the numerator over negative 1 to the n plus 1 factorial there in the denominator. Okay. So that's just the reciprocal of the term that we were given there. So question, Sean?
So, I know this might sound a little weird, but where did you get the x?
The x here and here.
Yeah.
So our Taylor polynomial, right, for this particular series or this particular function or whatever is defined by this. You're okay with that? Okay. So then the general term here is going to be represented by this.
So that's what we're.
So then we're doing the next term. So here's the next term right here. F n plus 1 derivative of f over n plus 1 factorial times x to the n plus 1. Okay, and then times reciprocal because we're going to divide by the previous term, just the nth term.
Right, why can't you use the function like at the top, like given?
Do you use just this?
Yeah, why can't you use that?
Because just this alone is not our Taylor polynomial. This is only describing the nth derivative of f at 0. So it's missing the other components, the over 1 factorial times x to the 1, over 2 factorial x to the 2, or the over 3 factorial x to the 3. It's missing those other pieces. We need to incorporate those as well.
Right.
Okay? Because also you'd lose your x here if you didn't. You need the x there because that's what we're going to be solving for eventually.
Yeah.
Okay? So I think I see what you're saying, but yeah, we need the x in there at least. Okay? So, all right. Are we caught up so far? Everyone feeling okay up to this point? Yes? Okay, or you just want to move on anyway, and you just don't want to ask me any questions because why prolong this torture and just, okay, well, anyway.
That's exactly right.
Oh my gosh, can Mr. Wade read my thoughts? I better stop thinking some things then. All right, so anyway, what can we simplify here? All right, so the 5s, that's right. So 5 to the n plus 1. That will simplify and leave us with just 5 to the 1 there. Okay. And then what else? Well, the negative 1 n plus 2 and the negative 1 n plus 1, we can kind of ignore those because, again, we're in absolute value, so we don't really care whether things are positive or negative at all. And so let's rearrange here. Let's group things together. So let's group our non-n terms together, right? Because that's what we typically do. So we have, well, what do we have for the non-n terms? In the numerator, it'll be what? X to the 1. Well, x to the n plus 1, but I canceled that earlier with the x to the n that was in the denominator. So just x to the 1 over, and then what's in the denominator? That's a non-n term. 5. So we have x over 5, and then times, and now I'm going to group all my n terms over here. So we have, well, let's see here. The n plus 2 factorial and the n plus 1 factorial, that's going to simplify to just what? Yes, so we can cancel out that and cancel that. We have n plus 2, but then that's times n minus 1 quantity squared over, and then we have n plus 1 times n squared. Okay. What do we know about this right here? It will go to 1. Wow. Isn't that? Look at that. Okay, and so that becomes then negative 1 less than x over 5 less than 1. Okay, and then we'll just multiply both sides by 5 here. Negative 5 less than x less than 5. Okay, and then we need to check our endpoints, right?
No.
No, because you don't want to?
Because we only need the radius.
Because we only need the radius. That's right. Not because we don't want to, but because we don't have to, okay? The radius is 5. That's all we needed was just the radius.
I thought we were about to have to.
That's it, yeah. Mike was like, end it now? No. R equals 5. We are going to end it now, Mike. Yes, exactly. Okay?
Class is over. You're welcome.
End that problem. All right. So now let's just like pause here real quick too. Okay. Understand, A wasn't that bad, right? B also not too terrible. C was pretty awful, but that is 1/3 of one free response question, right? And if these, let's just imagine, I forget what the points are. We'll come back to that. But let's just say that from these two, maybe you can get 6 points out of the 9. If you completely bomb this, if you can still get all the points here, right, and let's say that gives you 6 out of the 9 points, because it's like roughly 2/3, okay, right? I mean, maybe they would give you a few more points here. Let's just say 6 out of 9. You're on your way to a 5, even if you completely screw this up and have no idea what to do, right? Like, just doing these two, if it is 6 out of 9 points, which I'm guessing there's probably going to be a few more in here. Anyway, but it still is like not that bad that you'd only be able to do A and B there. That's still pretty good if you can just do A and B. Obviously, we want you to be able to try C and do it and stuff too. And it's there's just a lot going on there. So, Kara, question? Sorry.
How many FRQs on the test?
Sorry, say again.
Like how many FRQs and multiple
Six.
choice on the
Six free response questions, and I'll have to get back to you about the multiple choice because I think that changed like last year or something like that. So I just want to check to make sure on that. But there are 6 free response questions for sure. I think it's like 2 and 4. So it's gonna be. I have to check on that too. Whether it's 2 calculator active and 4 non-calculator, or vice versa kind of thing. That's 2 and 4. Okay, one more here, and this one I'm gonna have you guys try first on your own. Okay, so give it a go there. Okay, and give it a try, and I'll walk around and kind of help you out if you need a push, or if you want to just check something. So go ahead and try that one right there. And I'll pull up the scoring guidelines too so we can kind of see. Bless you. Oh, that's A, B, B, C. Bless you. Let's see. This part right here. No, that's perfect. Yeah, good job. Yeah, and then doing what you did right there. Yeah, now we go to 1. So it should be,
Oh, it should be less than.
right, you want to assume it's less than 1 for the ratio test. So you just have an absolute value of x, less than 1. And then so, right,
It has to go to a certain amount. I don't know. I'm just gonna skip it for now.
See what you have. What'd you get?
I should have her answer here. I don't know.
I got that or that. I just better check it.
I got Octo's trouble with the first term.
Yep. And then what do you get? 4 squared, x squared, and then 8x cubed minus x cubed. Yeah, and don't forget you all need to come up with these. I'll write 3 8 plus 7. Good. Don't forget to, yeah, good.
After you.
Okay. What's up?
So get it told here.
So,
Checking
sim,
negative one.
we did some, okay, so then, again, limit of what?
Go to share alternate.
It's F
Nope.
to the
So, same piece level in here, still have the values, right?
to the Z
And then this times opportunity there.
of the Z value over
Just define factorial.
So, I mean, sorry,
No,
the side,
over
like, mean, like,
n.
this and this kind of thing.
X
So,
n.
well, as n approaches infinity, you have
X-
where your top
X
is 1, your
minus
bottom
C
is 1, so it's gonna go to a ratio of least coefficients 1. So you're gonna have to do this with x. For the ratio test, you want it to be what?
So it has to be less
Less than 1, so you set less than 1 here, right?
So
So
we
that
have
means
to
you're
find
gonna
Z.
go half by x.
Z has
is
to be
less than 1.
between.
So it's out here, here, somewhere, you set half by x equals 1.
This is
And then you set up your interval, you know, then you write your interval.
increasing.
Okay? Is that good? Is that got you going where you need to go, or you're?
Yeah, so I know it needs to be.
That's between 0 and
Yes, but is this equation
That's
equal?
easy, so it always should be more bigger than one, so it would be 2 over 3.
Yeah. So,
Nope. Converge. The degree of this
It's
power
decreasing.
building, that's the power. These are degree zeros.
Decreasing,
So
so
the highest
it's
degree
increasing.
of these two, 1, 1.
Z.
And so the ratio of the coefficient of 1 over 1, which is 1. So x times 1.
I think it's his case.
Right?
Depends on what you plug in.
I guess the divergence.
And so then that means what's your actual interval? -1 less than x less than 1.
Madison.
F
How you doing?
Ratio test, so you can drop the absolute values. So then once you use the, since we use ratio test, we're going to do that. Actually, looking at
One third right here.
Okay, Mario, you got a question?
Yeah, alright, so with this,
Convergence.
enter,
Oh, I'm sorry, I thought it was negative there. It's, yes, it
so
diverges.
diverges, and this one converges
That
because.
one covered because it is divergent, because all that. Sorry.
on the bottom, it's a range error. It's F to N. With the value of.
The nth derivative of that, so it's the next term derivative of that,
Okay.
right?
To the Z.
At z, of z kind of thing.
Okay, and which
Then
value?
times x to the next term all over next term, you know, factorial.
Whatever that is. Okay, so I have a question. Would we use F, would N be 4 for this?
So let me just check on use the first, so we use the first 2 terms of the Maclaurin series for f to approximate f of 0.1. Okay, what I'm saying is use the first 2 terms, then the next term would be the third term.
So the third term is X to the third.
Over by so we gotta be careful. So it will be
So we think it's going to this.
right, exactly. What's going through my head? I'm like bit hang on, I hear what you're saying there, let me think.
If you use
Wouldn't
the
it be
first.
good, yeah, because we're using the first 2
So it's-
non-zero terms for. So approximate.
It's the next term of like the
Wait, wouldn't it be to the Z though? Wait, what was your? Half of N to the Z? Yeah. Right?
oh yeah. Yes. So like this is the format we're gonna use. It's like the next term of the Taylor. So In this case, it's going to be 3, right?
Yeah.
And so we already know what x is. X is given to us there. It's 0.1. So it's up to us to then come up with, that z value that's going to maximize.
Yeah.
Essentially, we want to find the absolute maximum of this. Absolute maximum of this. Well, you're getting some information about that third derivative. Always less than or equal to 2. So in other words, the absolute maximum the third derivative is always less than or equal to 2 on the interval from 0 to 0.1. What's that interval? That's the center to the point that we're evaluating. That's the c to x, kind of interval there.
Yeah.
So in other words, what's the biggest value of this that can possibly be? So z, right? We don't actually need to worry about finding z at all in this case. What will the maximum value of this thing be? 2.
Oh, 2 because.
So we don't need to worry about finding z in this case because the information we're given, we just know 2 is gonna be the highest it's gonna be
Okay.
on that interval.
So
then this is different, a little bit twisted from what we normally do. Right? Normally we figure out the z value, we plug the z into the third derivative, and then find what that absolute maximum value is. But in this case, we don't know what the third derivative is, but we do know that the absolute value of the third derivative is always less than or equal to 2 for this interval, and so therefore the maximum value is, just replace this top piece here with 2. That's all you gotta do. Yep, Sean?
How do you figure out z?
You don't need to in this case. You can buy this. If you did, you would figure out z based on whatever the third derivative of that
I
function
just did the
is.
second part.
Well, in the interval from your center to the x
Wait, what
value
is-
that you're evaluating.
I'm pretty sure it's.
This is like a graphing thing.
So you could use a
You
graph.
still have to tell the approximation.
You
Yeah.
may have to take the derivative of the third derivative and do the fourth derivative.
We have to. I think it's
So
zero,
the past times
zero.
we've had just the function themselves, oftentimes what's happened is when you get down to that third derivative, it's, oh, the third derivative,
I think
it's
this
always
is
the
how
so
you-
therefore it's the right hand point interval, so we're trying to use the. Okay,
You
use
can
the
one
use
is
the
one
left
and
point interval, and stuff like that.
wait, how do you find?
Yeah.
Is that right? Like I don't.
I mean that's technically.
The alternate one, yes, that one does, yes.
Okay.
How are you supposed to know that?
This one. You compare it to 1 over n
Exactly.
and 1 over n diverge.
1 over n diverge because that's p
Oh,
series
because-
p is equal to 1. This one, okay, will be in the same ratio of, of that.
1 to the n will always be.
So we found that now.
So that compares to so, sorry?
1 to the n will always be 1.
Is this calc active?
Or
1 n will always be 1, exactly, so you can make it 1 over.
Is this calc active?
This will be calc active,
So you
yes.
have-
Yes, sorry, this would be calculator active. My apologies here, folks.
It's all good, I'm on break.
It's all good, I'm on break.
Let's just go through that. That's a nice
quality
idea.
of these tissues.
Yes, it's like a 100 grit sandpaper maybe or something, so. It helps to eliminate the germs by scrubbing them off your face. Question.
Okay, so if we have a -2, like in parentheses, do we have to have the alternating series, or can it just be like -2 without?
You can leave it. You can leave with the negative in front there. It's just helpful for you to recognize that you can, pull that negative one out to see that it is alternating and stuff.
I can have a negative.
Oh my gosh, yes, you asked like a million years ago.
It's okay.
And then we have to find
I have like a variety in here, so I don't know if you want to like kind of like peruse them and see what kind best serve your purposes.
That's an approximation. Do you need to simplify the approximation, or can you leave this fraction one? Like 2 separate fractions?
Well, no,
You're trying to show that it differs by less than 1/5,
so that's
right? Oh wait, that's from the previous one. I'm sorry.
Difference by at most 1 over 3,000.
Okay, so you want to
That's
show
max error, right?
that would be your max error. And what does your calculation end up resulting in? Which is
I was born this way.
So good.
Yes. So, exactly. So you are fine. In this case, it's not like you're showing that it is exactly that.
The next term dies, and then figure out where the max is, and that's what I need to do.
Okay.
Is that all we need to do?
That's it.
So we just need to write that P2 of 0.1 is equal to 0.1 over 1 plus 0.1 squared over 4.
2 times 0.1 to the 3 over 3 factorial
Yeah.
for letter C.
And then that's it.
Yeah.
And then we're fine. Yeah.
Just show that that is, you
I just
know,
don't feel like it's complete. Like I don't.
1 3000. So, all right, folks, I'm going to show you the answers here. Okay, and then we'll go through the scoring guidelines real quick.
Oh, I actually found it. That's 43 over what?
Okay, 43 over 1,200.
1,200.
43 over 1,200. Yeah.
How'd you get 45?
Because
Just type in my calculator, hit math, enter. So, because it's calculator. Letter A, okay, so there's your answer. We did have to use a ratio test there, so please make sure that you did, -1 less than or equal to x less than 1, okay? The -1 is included because it's alternating. The 1 is excluded because it is, well, not. It's going to diverge by the limit comparison to 1 over n, because 1 over n diverges then, 1 over n plus 2 would diverge, okay? Letter B. Letter B, there are your first 3 terms, and then your general term, okay? If you have some sort of other, like, formulation of the general term there, that's fine, okay? You don't have to have it the way I wrote it, bless you. I do find it helpful, though, to separate your x, okay, from other stuff, okay, to have it kind of separated, but it's not necessary, okay? And then letter C, and then letter C, okay, letter C. So I found the precise value. Sorry, I didn't find the precise value. I found the approximate value of f of 0.1 by plugging 0.1 into the first 2 terms there. Okay, you end up with, if you simplify it, 43 over 1,200. But this is of course sufficient because it's just arithmetic. And then we do our error calculation here. Okay, now this one had a little bit of a twist to it because first of all we have to use Lagrange, right? We're told that use Lagrange error bound to show the approximation differs from f of 0.1 by at most 1/3000. Okay, so again, we set up our little error, and we just show this for display, really. Like, this is not a calculation we ever actually do. It's just there to show this is our error, okay, the actual error. We know that it will be less than or equal to this error approximation, right, the maximum error approximation. Please do set this up, okay, because in this case, it maybe would be helpful for you to see, wait a minute, I need to figure out what this z value is. Well, or at least normally we have to figure out what this z value is. But we have no information about what that third derivative of f is going to be, okay, right? We don't have we don't have a way to find that third derivative. We don't have what the actual function is that describes this. That's describing this series. So what do we fall back on? Well, we're given this little piece of information back here. Okay, right here, the third derivative of f at x is less than or equal to 2 for 0 less than or equal to x less than or equal to 1. That's our interval right there that we normally see, right? There's our c, center is 0. There's our x value of 0.1 we're approximating, so that's the interval. So for any, and they made x instead of z there. So the between the 0 and the 0.1, we know that this third derivative is always less than or equal to 2, which means the absolute maximum value of that third derivative is what? 2. And so then the absolute maximum error here, right, we're going to put a 2 in place of that and make it 2, and then 0.1 to the third over 3 factorial. And when you simplify that, you get 3.333333 repeating times 10 to the negative fourth, which is 1/3000. Okay, and so therefore we showed, of course, that yes, the error, okay, is going to be at most less than or equal to 1/3000. Okay, so in this case we found the, we showed the actual maximum error there. Okay, 1/3000. Okay. Questions on any of that? So I do want to just quickly show you the scoring guidelines for these last 3 problems that we did, okay, just because I think it's helpful, again, to see this. Okay, so I'm going to talk through these, and my apologies to those of you guys on the video because you won't be able to see this stuff. So let's talk about the one we just did, which I think I just put up there. Is that it?
Yeah.
Yes.
That's the very first one.
Very first one. Sorry. Let's do the one that we just did because I think that'll be more helpful. Because that's fresh in our minds here. Is this it right here?
This is not.
Nope, that's the wrong thing. What am I? 2015 scoring guidelines, question 6. This must be, oh, maybe I didn't do Form B here. Sorry, let me see here if I can find that. That was a different one. No, I did look up Form B. Oh, I wonder, I don't know if I was able to find, was I not able to find this one?
Wait, that?
Just Google some of the questions and it'll pop up. That's what I do.
That's what I did do, but. Okay, yeah, for some reason I can't find that one. Anyway, well, we don't have the scoring guidelines for that one. Okay, but I do have the scoring guidelines for other ones, so let me just show that then. Okay, so here's our very first one. Okay. So just kind of some things to point out here. You'll see for letter A, for the very first one we did, you get 2 points there. 1 for the first 4 terms, 1 for the general term. Letter B, 2 points for your answer with analysis there. Okay. Letter C, all right, you'll notice here you get 4 points for letter C. You get 2 terms. You get 1 point for just 2 terms for f comma t squared. You get 1 point then for the other term. So they kind of like break up the series there because they asked to do the first 4 terms, I think, Frank. They break it up and give you 2 points for each part, okay? And then for number 1, you get 2 points, or you get a point for the first 2 terms of g, and then 1 for your approximation, okay? So that kind of jazz right there. You can see how they kind of work. Okay. So just kind of interesting there. And then for letter D, just 1 point for the analysis. Okay. All right. Ooh, and I forgot to put. Shame on Mr. Widmeyer. So I forgot to put for letter D that we needed to say that it was alternating and the terms were decreasing absolute value to 0.
Minus 1
Wow.
point.
Yeah. So we didn't get that point. I did not get full credit there, guys.
Doesn't
Okay.
it state it in the statement?
Oh, did
In
it?
the question?
Oh, you're right. Never mind. It did state in the question, so we didn't have to worry about stating that. Okay. Thanks for the save, Lander. All right. So
+1.
+1. Back to 9 out of 9. Okay. And then there's the second one that we did. Okay. So you get 1 point for the answer there, which means ostensibly you could guess and get a point there, right? As long as you guessed wisely. You have 3 options, and it didn't say that the answer had to be justified, okay, right? It just says answer. So if you just guess relative maximum, you get a point there, okay? So understand that, right? When you're doing the free response, sometimes you can guess. It's like kind of multiple choice there in that free response. And then letter B here, you get 3 points for that Taylor polynomial. And you notice you get -1 for each incorrect term. Okay.
So could you get negative points in this question?
No, but you would just if you made one little mistake in one term and then another mistake in the other term, maybe a different one, and another mistake in the other term, you lose points, even though maybe they were kind of tiny errors and things. And of course, if you look at this, you lose points for giving extra terms. All right, so don't try and be impressive there. Okay, don't try and do more than you need to. You lose a point for giving extra terms. So don't give more than you need to, or you will lose points. Okay. All right, and then there's letter C. Okay, so in this case, right, you would have gotten 5 out of the 9 possible points if you just got A and B, right? Letter C was this hot mess. All right, but I mean, if you look at it, right, I mean, you do get some points here. Just for writing the general term, 1 point for just setting up the ratio, okay? So again, you can get points out of this. Even if you look at this, you're like, I don't know if I could have ever gotten that 100% correct. You don't need to, okay? Again, your goal for these 3 responses, 6 out of the 9 points. If you get that, you are on your way to a 5, okay? So again, very doable. Get your points where you can and stuff like that. Okay. So let's see. Yeah,
So
Dave?
you get a 6 out of 9 on every single free response. You get a 5.
So what I mean is you are on track to get a 5, okay? Because your goal for the overall test to get a 5 would be a 66% roughly. 6 out of 9 points on all the free response questions, but also then a 66% on the multiple choice too is what you want to shoot for as well. So I'm not going to say, obviously you have to do well on the multiple choice too, or well as in 66%. But if you can maintain that for the whole test, that's a 5. That's on the way to a 5, okay? So it's very doable, but again, it's, well, you got to make sure you get those points.
If I get a 66% on an answer at 5.
Okay. Your homework, right. Your homework, let me get you that here.